This reduces the effects of post-exercise and allows the functioning of the muscles to be maintained. Here we have some examples of cryotherapy that use different techniques, but overall they all help to control and cause vasoconstriction of the muscles, which decrease the tissue metabolism and force blood through to remove the damage, inflicting waste from your system. This then decreases the pain and muscle and reduces the risk of spasms developing. Particularly in submaximal sports like the 1500 metres, at the end of the race the athlete's muscles will have fatigued due to the prolonged event and therefore will be painful and exhausted. The build-up of waste products like lactic acid would need to be removed in order to reduce the risk of cramping and injuries. Ice massages and baths will be particularly useful and help to hydrolyse the lactate accumulated to help move it more efficiently. But also, in contact sports like boxing, it can be extremely important because it has similar effects to painkillers. The ice packs can be used during the match to reduce the inflammation to a particular area. Then after the match, the ice baths can be used for the whole body in order to reduce DOMS after high intensity exercise. And here are just some other examples as well that can be used in order to combat the effects of fatigue. Now we are going to be looking at recovery in different sports of different intensities and analyse the causes and strategies that are used to help a performer recover. It is important to understand that recovery doesn't just occur after exercise, but during the sports also. This is because different sports have different demands that vary and therefore require different substances from recovery. If we consider a sprinter, because their event is working at a maximum intensity for a short duration, they don't have time or even need to fatigue during the period. As after it is over, the athlete has sufficient time to recover, as their next race may be days after. Whereas if we consider a basketball player who is constantly working aerobically and anaerobically, and due to the high intensities that need to be maintained, they're mainly using their ATP-PC system, so they need to replenish these stores in order to be able to sprint while dribbling the ball and when trying to regain possession. So these athletes have to try to recover during their play in order to try to maintain their intensity. In basketball, they have a timeout which the players can use that lasts for about a minute, and in this time they are quickly trying to recover and replenish their PC stores so they can continue. And this whole sort of concept of trying to maintain the stores is known as glycogen sparing. So the athletes can train in order to burn more fats to preserve the glycogen stores for exercise. And so recovery in different intensities is different, and we can see that anaerobic activities, as shown by the diagram, can take up to around 10 seconds to a minute in order to recover, while the aerobic activities take much longer. This is because the duration is prolonged, so therefore the amount of strain being put on the muscles is longer, so it's going to take much longer in order to remove the waste products built up and sort of just recover from the exercise and the strain it puts on the body compared to that of a sprinter, because their event is over quite quickly, so they don't need as much time in order to recover, because their stores, although they're depleted, they can be easily recovered quite easily. Now we are going to be looking at the concept of Epoch. Epoch is the excess post-exercise oxygen consumption. This means the overall oxygen volume consumed after exercise in the post-recovery phase. It occurs as shown on the graph when exercise becomes anaerobic, and therefore the energy is now being converted to the anaerobic system in the recovery period. It involves extra oxygen consumed due to the fact we are breathing faster and deeper following exercise in order to try to increase oxygen in the body to return to pre-exercise state, where our body is most comfortable. From the graph on the left, we can see that before exercise we are not consuming much oxygen, but as we start to exercise, the box with E and C shows how much oxygen we need for the activity. Particularly C represents the amount of oxygen we consumed during the event, and E is the oxygen deficit, which is the amount we failed to take in. and this is known as the anaerobic effort. So we can see that at rest we are breathing normally, it's quite shallow, but as we start to exercise we can see that we are working much harder and therefore we are breathing faster, but the demands overtake the oxygen we are consuming and therefore we start to develop an oxygen deficit. Then from A we experience Epoch, which is after exercise, so now we're in the recovery phase. This is the oxygen needed to get back to pre-exercise state in order to repay the deficit we have accumulated, and this is then split into fast and slow components. The fast component, known as the A-lactacid of Epoch, occurs in the first 2 to 3 minutes of recovery, which is represented by A on the graph. It takes around 1 to 4 litres of additional oxygen in order to help to resynthesize ATP, PC and myoglobin to reduce the fatigue. Even though it takes 3 minutes, we actually synthesize 50% of our PC stores in around 30 seconds, but it takes another 2 minutes in order to resynthesize the other 50%. Part D on the graph represents the slow component, the lactacid system, and this takes longer to remove, hence why it's known as the slow component, in order to remove the lactic acid and maintain ventilation and body temperature. This requires an additional 5 to 8 litres of oxygen, which can take up to hours depending on the intensity and lactate accumulated, in order to reduce the elevated levels to remove carbon dioxide and increase oxygen delivery. Also to allow a decrease in body temperature over a longer period of time so it is slow, so we don't lose too much heat. When we react lactic acid with oxygen, we can then convert it back to pyruvate, back into the Krebs cycle, into carbon dioxide, glucose, protein and water during the slow component, so it can be utilised in the body. And we can see from the graph that the athlete's ventilation rate has remained elevated after exercise. And this is what we would expect to see with heart rate, because it's helping more oxygen to be breathed into the body and help break down the lactate which has been accumulated over the exercise into more useful products like we mentioned, and to replenish the ATP and PC stores and repay the oxygen deficit in the body by supplying hemoglobin and myoglobin with sufficient oxygen so they can continue to function. Recovery is extremely important to a performer, and if the muscles do not receive adequate recovery time, they will become too exhausted to contract to meet the demands, so the performer will then start to experience some of the effects of fatigue. This is why after strenuous exercise, there are 4 main processes which the athlete must undergo in order to allow the muscles to then fully engage to their maximum again. The first factor is the resynthesis of muscle PC stores, and this is to do with the A-lactacid component, where it coordinates restoration of muscle phosphagen. This involves using the extra oxygen to help resynthesize ATP into ATP and PC by joining the phosphate back to the molecule. This process is quick and takes around 2 to 3 minutes, so this can then be reused again to help the athlete, while to remove lactic acid takes around 20 minutes until the muscles can function well again, and to replenish the myoglobin takes over 24 hours, but it can vary with the intensity of the exercise. So athletes that have been working at high bouts of anaerobic exercise will then take longer to recover than those who are working at a lower intensity. This is because the lower intensity sports can repay their oxygen deficit more easily, and therefore their stores are not completely depleted. And here on the screen we just have some of the factors that the A-lactacid and lactacid components help to combat in exercise. So here we have 2 graphs showing Epoch in different intensities in exercise. On the left we have submaximal exercise, and on the right we have maximal exercise. So if we compare these graphs, we can see that in submaximal exercise, this athlete is experiencing a much smaller oxygen deficit than the maximal exercise. This is because they're using the aerobic system, and therefore they have achieved steady state. So that means the oxygen consumed is meeting the demands of exercise, and therefore they are not having to convert to using their anaerobic system in order to produce energy like they do in maximal exercise. So for example, a marathon runner would be working at steady state because they've balanced the demands of their oxygen consumption, whereas a sprinter would be working anaerobically without oxygen in order to produce the maximum force, so therefore their oxygen deficit would be much higher. And we mentioned that submaximal exercise, they're working at steady state, they've balanced the demands, so the VO2 required for exercise matches the VO2 max. And this isn't the case in maximal exercise. And in submaximal exercise, the athlete is working mostly aerobic, so they're respiring aerobically. So this means less lactic acid is produced as a result. So their epoch their recovery would be much more efficient and probably be much quicker because the waste products are not being produced as much as they are in maximal exercise. So the slow component would not be having to be much more effective than in maximal exercise. And in submaximal exercise, there is a quicker recovery due to the fact that less VO2 is consumed than that in maximal exercise. So therefore, this makes recovery more efficient because, like we said, the oxygen deficit does not have to be repaid because their VO2, the ventilation and the amount of oxygen taken in is meeting the demands of exercise. So if we just look at this from the perspective of the maximal exercise, this means they have a larger oxygen deficit than the submaximal exercise, and we explained this. They don't achieve steady state because their event is so high duration. Hydration is over very, very quickly. They don't really have time to match the demands of oxygen with the exercise. So therefore they are respiring anaerobically. So more lactic acid is produced and hydrogen ions. Therefore their recovery, the slow component, takes longer in order to remove these waste products. So therefore they have a larger epoch. So the VO2 is consumed in recovery. There needs to be a larger volume of oxygen in recovery in order to replenish all the stores than there is in submaximal exercise, and therefore this makes the recovery slower. So it takes longer for them to replenish their stores. Now we're going to look at oxygen deficit in a bit more detail, and we have a graph to demonstrate this on the screen. So we can see that our oxygen consumption compared to our exercise, so as we begin to exercise, our oxygen consumption increases, and therefore we can see that we are obviously taking in more oxygen during exercise, but obviously more is being used due to the demands of the muscles and the respiring tissues and organs of the body. So therefore we are experiencing an oxygen deficit. This has a negative effect on the body, where it's not receiving the amount of oxygen needed to meet the demands of exercise. Therefore, the performer is starting to work without oxygen and therefore will be using the glycolysis system in order to produce ATP. However, this system is limited in its duration, and if the athlete tries to sustain this intensity, they will be forced to stop due to the waste products produced. This is where the graph starts to decrease. But during recovery, the athlete is trying to repay the oxygen deficit, which is where the body has a deficiency of oxygen. This requires the extra oxygen in the oxidative energy processes in order to convert the lactic acid into glucose and depleted ATP and PC stores to be replenished. It is measured as the volume of oxygen needed after vigorous muscular exercise compared to the volume needed at resting state. This is why our breathing levels and heart rates remain elevated, as it takes time after the exercise in order to replenish the stores and replace the oxygen. And we don't want to deplete these levels too quickly, as it can have negative effects on the body. So by the levels remaining elevated means we can adequately account for the body and make sure that we can remove heat at